Are you looking for a good problem that deals with inference for the difference between two population means? Well, you've come to the right spot. This is question number 4 from the 2018 FRQ exam. Full answers explained. Let's dive right into it. The anterior cruciate ligament, known as the ACL, is one of the ligaments that help stabilize the knee. Surgery is often recommended if the ACL is completely torn and recovery time from the surgery can be lengthy. A medical center developed a new surgical procedure designed to reduce the average recovery time from this surgery. To test the effectiveness of the new procedure, a study was conducted in which 210 patients needed surgery to repair a torn ACL were randomly assigned to receive either the standard procedure or the new procedure. Part A. So before we read Part A, quick idea here. This is basically doing an experiment. They want to see, does a new procedure help recovery time be faster from an ACL injury versus the standard ACL procedure? Pretty simple, right? It does sound like they're going to do an experiment. Doesn't go into extreme detail, but got 210 patients. Some are randomly going to get the new procedure. Some are going to get the old. Based on the design of the study, would a statistically significant result allow the medical center to conclude that the new procedure causes a reduction in recovery time compared to the standard procedure for patients similar to those in the study? So the key idea here is that it says, could a statistical result allow us to use the word cause? Can we say that the new procedure will cause a less time to recover compared to the standard procedure? Now, remember, we are allowed to use that word cause only if we have a well-conducted experiment. Now, there's not a ton of detail here, but it does sound like they're doing an experiment, and you got to trust that they're going to follow all the rules to a good experiment. Therefore, we can use the word cause. So if we do find out that the results were statistically significant, meaning that they did not happen by chance, and that the time it takes to recover from the new procedure is significantly faster than time for the old procedure, we can say the word cause. So the answer to this question, first and foremost, is yes. It would be reasonable to conclude that the new procedure causes a reduction in recovery time for patients similar to those in the study. The patients were randomly assigned. So that's why, right? Because they want you to explain your answer. So why am I saying yes? Because we have random assignment. In an experiment, the key idea is that you have random assignment of the subjects to go into each of the two groups. So random assignment of the subjects is a key to being able to conclude that cause and effect relationship. Now, this last part is really not something you have to say, but I think it's important to note that the 210 patients may have been volunteered to be in the study, which is why we need to say that the new surgery can cause a reduction in recovery time only for those that are similar to the patients in this study and not all patients. Please do not say, oh yeah, this is true, this is great, this new surgery is going to work for all patients getting an ACL tail surgery. That's not necessarily true, because in an experiment, when you use volunteers, you are allowed to use the word cause as long as you have that random assignment, but you can't infer your conclusion to all people. You can only infer to people similar to the ones that volunteered to be in your study. So hopefully that makes sense. So pretty easy part A there. Now part B says, well, here's the data. We actually had 110 people get the standard surgery, 100 people get the new surgery, and here is the recovery time in days. I'm assuming we had a doctor that actually cleared them, so it was not just their own personal feeling of, yeah, I'm ready to start going and playing soccer again. So we have the mean recovery time for the group that got the surgery that was standard and the mean and standard deviation for the group that got the new. So do the data provide convincing evidence that those who received the new procedure will have less recovery time on average than those who receive a standard procedure? So first we have our sample sizes, N and N. So that would be N new versus N standard procedure. Then we have the mean for our standard procedure and the mean for our new procedure. So just based on looking at those numbers, it does seem that the mean of our sample was longer than the mean of the new surgery group. And we also have our standard deviations for the standard procedure and our standard deviation for the new procedure. Now, just saying, well, 217 is greater than 186, case closed, looks like the new procedure is going to require a faster recovery time. Well, come on, we know that that's not good enough. We do have to actually conduct a test here because they do want us to look if there is convincing statistical evidence. All right, so this is a 4-step process, as you should already know by now. So step 1 is naming it and giving the hypotheses. So this is a 2-sample t-test for the difference between the mean recovery time of those with the new procedure and those with the standard procedure. So make sure you talk about the fact that this is a difference between the mean recovery times for each of the 2 groups. Now, why am I using a t-test? Because I don't know the standard deviations of the population. I only know the standard deviations of my samples, which is why we have to use a t-test instead of a z-test. Now for my hypotheses. The null hypothesis would say no difference. The true mean for the standard procedure is equal to the true mean for the new procedure. There's no difference in the recovery time. And the alternative is what I'm hoping to show, that the mean for the standard procedure is greater than the mean for the new procedure, or actually you could say it the other way around. You're hoping that the mean for the new procedure is less than the mean for the standard procedure. It would obviously be the exact same thing. All right, now step 2 in conducting a statistical test is to check the conditions. That way your sampling distribution that shows all possible sample differences will be normal. Now, the center is going to depend upon the fact that we do have that random assignment, right? So we do have to have random assignment of what subjects get into what group to avoid bias. Now, the samples are independent of each other. We actually already know that because we specifically put 200 people into one group, or excuse me, 100 people into one group and the other 110 into another group. That was done randomly, but that instantly makes them independent of each other because one person cannot be in both groups at the same time. Furthermore, the distribution of the sample differences is assumed to be normal because both samples are definitely sufficiently larger than 30. The one sample is 110, one sample is 100. As long as we're 30 or larger, we can assume that our sampling distribution will be normal. Now, the other thing I actually need to do here is build that sampling distribution. So what is the mean of all possible differences between the new procedure and the standard procedure? Well, I have to assume the null is true, which means that if the null is true and there is 0 difference between them, they are in fact equal, then that would give me a mean of 0. So I would assume that the center of my sampling distribution, if there is no difference between these 2 procedures, would be a 0. I now need the standard error for the difference. Wish I could use standard deviation, but unfortunately all I know is the standard deviations of my sample, so I'm going to be using standard error here. And it's not too complicated of a formula. It is on your formula sheet, but we're going to need the standard deviations, so that's the 34 and 29. So here we have 34 squared divided by 100, and here we have 29 squared divided by 110. Just to make sure that you got those correct, the 34 is with the 110, the 29 is with the 100, which actually, I'm glad I checked because I think I had that wrong. The 34 is with the 110 sample. So that's actually a very common mistake. Of course, I did it on purpose, right? That kids will mix up those numbers. Now, it's going to give you a slightly different value, so just be careful that you don't accidentally mess those up. Again, the 34 is the standard deviation for the group of 110. That was the standard procedure. The 29 was the standard deviation for the group of 100. And again, those numbers need to be squared on top and then divided. So just grabbing my calculator, showing how to get those actual values here. So I'm going to go and grab my giant square root. So we have 34 squared divided by 110 plus 29 squared divided by 100. And one question you may be asking is, why didn't they just do, 105 and 105 for the 210 people? I don't know. That would have made a lot more sense, but no one ever said that the 2 samples had to be exactly equal inside as long as they were randomly assigned. So we get a standard deviation, or standard error, of 4.34. Well, if we round, that'd actually be 4.35. So 4.35 is my standard deviation. Feel free to keep more decimals there if you want. All right, so I assume there's no difference in the middle, and I have a standard deviation of 4.35 minutes going both sides there for my sampling distribution. Those numbers are going to be needed here in step 3. So step 3 is actually find the test statistic and the p-value. So what was the difference between my 2 samples? Well, I had a sample of people that were using the new procedure, and I had a mean, and I had a mean for those using the standard procedure. So let's go back and grab those numbers out of my chart. So that would be 186 was the new procedure mean, and 217 was the standard procedure mean. So that's 186 minus, again, make sure you get these right, 217. And voila. Now grab a calculator if you want to actually calculate that difference. 186 minus 217. Whoop, and I typed that in wrong. Boy, oh boy, this calculator, man, it does nothing but give me fits. All right, so that's a difference of 31. Now, I actually did it in an order that gave me negative 31-minute difference. If you did it in the other order, you would get positive. Not going to be a huge deal. You could do it either way. I'm going to talk about the small change that that's going to make. Now I'm going to need my t-score, so I'm going to take the mean difference I saw of negative 31 minus the mean difference I expected, that's the mean, that would be 0, divided by the standard deviation that we calculated. Excuse me, I did it again. Standard error. I wish I could use standard deviation, but again, all I know is the standard deviation of my samples, which is forcing me to use standard error, 4.350. And now I'm going to go and grab my calculator here. So I have negative 31 divided by the 4.350. Obviously, I don't have to subtract 0. Hopefully, you guys understand that. And I get negative 7.126. Now, my p-value is the probability of this observed difference occurring or more extreme. So how do I notate that? It's the probability that any other difference between a sample of the new procedure and the mean sample for the standard procedure is even lower than mine. Now, if you used a positive 31, you would look even greater than it, because positive, you'd look even greater. So that's what the difference would be if you used a negative versus using a positive. And this is found by doing the probability that a z-score is more extreme. Uh-oh, I messed it up. More extreme in my scenario would be less than, because I'm negative 7.126. So now, the other piece of information here is I do need to use the t-model for this, and the t-model does depend on a certain number of degrees of freedom. Now, there's a couple different ways you could calculate the degrees of freedom when working with two samples. There is an actual mathematical formula that's going to give you some crazy decimal amount of degrees of freedom. The other thing you could do is you could actually look at the two different degrees of freedom. So I have 109 degrees of freedom here, and I have 99 degrees of freedom here. So you could use the smaller of the two, or you could add those 2 degrees of freedom together and do 99 plus 109. And you would use 208 degrees of freedom. So you could use the official formula, which I'll be honest, nobody uses because it's so ugly. You could add the 2 degrees of freedom together to get 208, or you could use the smaller of the degrees of freedom, 99. I'm going to use 208. It really is his preference, but most of the time, I'll go ahead on a leash here, or out on a limb here, and say that all the time it's not going to make a big difference to your conclusion. Now, when I go to my calculator, I'm going to need the t-CDF here. So I'm going to scroll down to number 6, t-CDF. I'm going to start at negative 99 because I'm going to look way below my z-score of negative 7.126. And then I got to type in those 208 degrees of freedom. And I get a p-value of 11 zeros, 833. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 833. That is an extremely low p-value. That means my sample was extremely significant. So the only conclusion is, since my p-value, and I should add that p-value in there, of 0.00000000000000833, and I might have missed a 0 there. Sorry, but anyway, since my p-value is way less than 0.01, I will reject the null hypothesis. There is... I don't know why it says is there. Sorry, it should start off with there. There is, I just had it in the wrong order. I'm bad at typing. I need to go back to English class. There is significant evidence that for those patients similar to the ones in the study, the mean recovery time for those with the new procedure is less than the mean recovery time of those with the standard procedure. So I'm actually concluding what I was hoping to conclude. And again, just make sure you use the word mean. It's the mean recovery time. I'm not saying that every individual that uses the new procedure is going to be faster. It's the mean recovery time for those with the new procedure is less than the mean recovery time for those with the standard procedure. So if you have a torn ACL, you might want to ask your doctor about a new procedure, so that way your recovery time is faster. This is fictional, by the way, so I don't even know if that's actually true. All right. Awesome, not too bad. Hopefully that all makes sense and you understand of my 4-step process to the significance test, starting off with the hypotheses, building that sampling distribution, getting that p-value, and actually concluding the test. All right, see you in the next solution video.